Right now, somewhere, someone is typing, "Hey Claude, build me an app," and it just does it. No syntax, no semicolons. No spending 3 hours looking for one missing bracket. Just vibes. But 70 years ago, programming meant feeding a computer stack of cardboard cards with holes punched into them. And before that, you literally rewired the machine by hand. So, how did we go from physically connecting wires to talking to computers like their co-workers? The answer is basically the entire history of programming. Because every major breakthrough did the same thing. It removed one more annoying layer between what a human wants and what a computer actually understands. And weirdly enough, that story starts before computers even exist. In 1804, a French inventor named Joseph Méry builds a loom controlled by punched cards. The idea is simple: hole, do the stitch; no hole, skip it. Change the pattern of holes and you change what the machine does. The instructions are no longer permanently built into the machine. You can swap them out, and that idea is going to become very important. Fast forward to 1843. Lovelace writes an algorithm for a computer that doesn't even exist yet. Charles Babbage had designed something called the analytical engine, basically a mechanical general purpose computer, except he never finished building it. So Ada was writing software for unreleased hardware. She's widely considered the first computer programmer in history, and she never even got to run her own program. Then in 1890, Herman uses punched cards to process data for the US Census. His company eventually becomes part of another company. You might have heard of it, IBM. And then electronic computers finally show up. Machines like ENIAC are insanely powerful for their time. But programming one, you are not opening a laptop. You are not typing code. You are physically connecting cables, rewriting plugboards, and flipping switches. And the people who figured out how to program ENIAC? 6 women mathematicians. They had to take a problem, break it into individual operations, figure out exactly how information should move through the machine, and then physically configure the computer to do it. So programming exists, but the interface between humans and computers is basically wires. That's pain number 1, and eventually we remove it. Instead of constantly rewiring the computer, instructions can be stored and fed into machines. By the 50s and 60s, that often means punched cards. Better. But now your entire program is a literal deck of cardboard. Hundreds, sometimes thousands of cards, all in the correct order. Drop the stack? Congratulations, you just invented the original merge conflict. So we removed the wires, but there's still another problem. The computer speaks machine code. Humans generally do not. So programmers have to write instructions as incredibly low-level numbers and operations. The computers love it. Humans hate it. And that gives us the next breakthrough: assembly language. Instead of remembering walls of machine instructions, programmers can use short words like add, move, and jump, etc. Underneath, the computer is still doing the same thing. But now, the instructions have names humans can actually remember. Still brutal, but at least it's brutal in English. One layer of pain gone. Except, assembly creates another problem. You still have to think like the computer. Every tiny operation, every register, every movement of data. You're basically micromanaging electricity. So in the 1950s, Grace Hopper works on one of the first compiler systems. And the idea behind a compiler sounds completely obvious today, but back then, people thought it was ridiculous. The idea was, what if humans wrote something easier and the computer translated it into the machine code automatically? In other words, what if the computer handled the annoying part? And this changes everything, because now programming languages don't have to be designed around what the machine finds convenient. They can start being designed around what the humans find convenient. And in 1957, FORTRAN arrives, short for Formula Translation. Scientists and engineers don't want to think about registers, they want to write equations. So FORTRAN lets them write something much closer to actual mathematicians, and the compiler figures out the machine instructions underneath. The computer adapts to the scientist, not the other way around. Another layer of pain gone. Then in 1958, John McCarthy creates Lisp at MIT for artificial intelligence research. Yes, 1958, AI research. Computers still take up entire rooms and people are already asking, okay, but can we make this thing think? Lisp gives researchers a powerful way to work with symbols, lists, and ideas instead of just crunching numbers. Different problem, different abstraction. Then businesses start using computers and businesses have their own problem. The people dealing with payroll and inventory do not want software that looks like alien mathematics. So in 1959, COBOL arrives and COBOL tries to make business code read almost like English, which sounds ancient now until you realize some of that code is still running critical banking, insurance, and government systems today. Think about the progression. First, programming meant physically rewiring the machine. Then we moved instructions onto cards. Assembly gave machine instructions names. Compilers automated the translation. FORTRAN let scientists think in formulas. Lisp let researchers work with symbols. COBOL let businesses express business logic in something closer to English. Every step does the same thing. The computer handles more of the annoying details, so the human can focus more on what they actually want. But there's a side effect. Programming gets easier, so people write more software, a lot more software. Programs get bigger, teams get bigger, and by the late 1960s, things are getting messy. Projects are late, budgets explode, bugs are everywhere. We solved the problem of writing more code and immediately created the problem of managing all that code. This becomes known as the software crisis. So the next layer of pain to remove, chaos. Languages like Pascal push programmers towards cleaner, more structured code. Then in 1972, C arrives and C hits a sweet spot. It gives programmers more abstraction than assembly without taking them too far away from the hardware. Fast, powerful, portable. And suddenly you can write an operating system like Unix in a language that can be moved between different machines without writing everything from scratch. The pain being removed now, being trapped by one specific computer. And C becomes ridiculously influential. Operating systems, embedded devices, cars, phones. But while programmers are getting better tools for building software, there's another problem. Data. Companies are collecting mountains of it, and getting information back out is annoying. So SQL changes the interaction again. Instead of writing an entire custom program just to find some records, you basically ask, give me everything from this table where this condition is true. You describe what data you want, the database figures out how to get it. Notice what's happening. We're slowly moving from telling computers exactly how to do something towards simply telling them what we want. Keep that in mind because that idea is going to come back. Then computers become personal. And suddenly software isn't just for scientists, governments, and giant companies anymore. Millions of normal people are using computers, which means millions more people want to build things for them. But software is getting enormous, so programmers need better way to organize it. Smalltalk helps popularize object-oriented programming. The basic idea, instead of treating a giant program like one endless pile of instructions, group related data and behavior together into objects. Then C++ brings those ideas into the world of C-style performance. Another pain point reduced, managing increasingly massive software. Then comes Python. And Python asks an almost insulting question. Why does code have to look so complicated? Python is designed to be readable. Less visual noise, less boilerplate, code that looks closer to pseudocode. The pain being removed now isn't the machine, it's the language itself. Then Java attacks another problem. You write a program for one kind of computer and it doesn't work on another. So Java's big promise becomes write once, run anywhere. Write the code once and a virtual machine handles the differences between systems. Again, the programmer deals with fewer details, the machine deals with more. And then the internet explodes. Now everyone wants a website. HTML gives the web its structure. And yes, before the comments start, HTML is not technically a programming language, I know. But the websites are mostly static. So in 1995, JavaScript shows up. Brendan creates its first version in about 10 days. 10 days. And now it runs basically every browser on earth. That escalated quickly. Then languages like PHP and Ruby make building web applications faster and easier. The barrier keeps falling. You no longer need to be a giant company with a computer science laboratory to build software. One person with a laptop can build something millions of people use. And then software gets even bigger. Now we are running global services across thousands of machines. So new languages attack new kinds of pain. Go tries to make large concurrent systems simpler. Rust attacks one of programming's oldest nightmares, memory bugs. Kotlin and Swift clean up mobile development, and TypeScript looks at massive JavaScript applications and says maybe letting everyone do whatever they want was a mistake. So it adds more structure, more types, more guardrails. Which is funny because after decades of carefully adding better structure to programming, we arrive at the 2020s and apparently decide forget all that, just vibes. At first, AI helps programmers complete individual lines, then it starts completing functions, then entire files, and then something fundamental changes. You stop describing the solution in code and start describing the problem in English. Build me a login page, connect me to a database, find the bug, make the button work, and the AI handles the translation. Which should sound familiar because we've been doing this for 70 years. Assembly said stop writing raw machine instructions. Compiler said stop translating everything yourselves. FORTRAN said just write the math. SQL said just tell me what data you want. Python said code should be readable by humans. And now AI says why write the code at all? Just tell me what you want. That's the part that makes this whole history so weird. AI coding feels like a completely new era, but conceptually, it's the same trend we've been following since the beginning. Every generation moves the human one step farther away from how the machine works, and one step closer to simply expressing intent. We went from physically rewiring the computer, to machine code, to assembly, to high-level languages, to readable languages, to natural languages. The gap between what I mean and what the machine does keeps getting smaller. And maybe natural language isn't even the final step. Because if the entire history of programming is about removing interfaces, then keyboards might eventually become just another interface we remove. Brain-computer interfaces are already being developed that can let some people control computers using neural signals. We are still extremely far from just thinking, build me an app, and having an app appear. But zoom out all the way. Once changing what a machine did meant physically changing the machine. Then we punched instructions into cardboard. Then we typed commands. Then code. Then prompts. And then maybe one day we won't even need to type. Because the entire history of programming has really been one long attempt to solve the same problem. How do I get this machine to understand what I mean? And every new language gave us a slightly better answer until now, when the programming language might just be language. And thanks for watching Nerdtic. And if you liked this video, please drop a like and subscribe.